In this section, we're going to learn another technique we can use to solve those maxima and minima problems. So if you think back to the previous section, we found maximums and minimums by finding critical points and then using our second partials to test those critical points. In this section, we're going to use a technique called Lagrange multipliers. So let's start by just considering an example, and I'll try to explain how this process works. So let's say we want to maximize the function f of xy equals xy. So I'm trying to find the maximum value of my multivariate function, and then I'm given a constraint such that 2x plus y equals 4. Okay, so one way that we can think about this problem is I can graph my multivariate function by creating a contour map or level curves. And that's what I've done in red here. So the red lines on my image are level curves for my multivariate function. The constraint, this line 2x plus y equals 4, is graphed in blue. Okay, so in red is my level curves, my constraint is in blue. And so the idea is we're trying to find the largest z value or the largest level curve that satisfies or touches my constraint, my blue line. And it turns out that the level curve with the largest c value that's actually touching the constraint or satisfies the constraint is actually tangent to that constraint. And you can see that in my image. Right here, my level curve is tangent to the constraint. That would be the largest z value along that blue line. So why is this important? What does this mean? This means that the gradients are parallel at that point. Okay, so the gradient vector for my constraint and the gradient vector for my level curve have to be parallel or scalar multiples at that particular point. Mathematically, this sentence, the gradients are parallel, can be written as the following equation. If I take the gradient vector of the function I'm trying to optimize, it has to equal a scalar, which we're going to use the Greek letter lambda for, times the gradient vector of my constraint. Okay, so the gradient of the function we're trying to optimize equals some scalar times the gradient of our constraint. And that lambda, we're going to call that our Lagrange multiplier. That's the name of that. All right, so I think now I just have written out what I tried to say in words. Lambda is my scalar. So gradient of our function equals a scalar times the gradient of the constraint. Okay, so what does that mean in terms of using a method to solve these problems? If we want to optimize a function f with the constraint g equals some constant c, we can set up the following system of equations. The idea that the gradient of function f is this vector with its partial with respect to x, partial with respect to y. The gradient of our constraint is the vector partial of g with respect to x, partial of g with respect to y. And then if gradient of f equals lambda times gradient of g, we can write that as two equations. Partial with respect to x equals lambda times partial with respect to x for g. Partial of f with respect to y equals lambda times partial of g with respect to y. So those first two lines right there are basically this idea that our gradients are parallel. And then we have a third equation, and that's basically our constraint that was given to us in the problem. So we can set up this system of equations and we can actually solve it. And we can solve the system of equations for x and y. And then the solution points that you get are going to either be maxes or mins. All right, so let's do an example. Let's do the same example I brought up when I introduced this idea. Let's see if we can maximize the function xy such that 2x plus y equals 4. So my constraint is the 2x plus y equals 4. I'm going to call that function g. So I'm going to say function g is 2x plus y equals 4. The gradient of that function g, derivative with respect to x is 2, derivative with respect to y is 1. So gradient is 2, 1. And then function f is the function xy. So its gradient vector would be y, x. Those are my partial with respect to x, partial with respect to y. So that means my system of equations is going to look like what I have on the screen. So I'm just going to take f sub x equals lambda times g sub x. And then my second equation, I take my f sub y, and that equals lambda times g sub y. And then the third equation in my system is just simply that constraint, 2x plus y equals 4. All right, so there is a system of equations. I have 3 equations and technically 3 unknowns, x, y, and lambda. And so I'm going to go ahead and try to solve this. And so I usually, how I solve it kind of depends on the equations I have, but I typically use some type of substitution method. And so I notice that this middle equation here is basically saying that x equals lambda, or lambda equals x. And so I'm going to take that and I'm just going to plug that into my first equation. So if lambda equals x, then the first equation turns into y equals x times 2, or y equals 2x. Okay, so if I use substitution on these first 2 equations, I get y equals 2x. And then I'm going to go ahead and I'm going to take the y equals 2x and plug it into my constraint. So I'm going to replace the y in the constraint with 2x. And then I get 2x plus 2x equals 4. So 4x equals 4, or x equals 1. Okay, so x is 1, and then if y is 2 times x, y is going to be 2. 2 times 1 or 2. So in this case, I only found one solution point to this system of equations. And this solution point is either going to be a max or a min. Now, is this a max? I hope so, because that's what they were asking me to find. But the easiest way to determine if it's a max is you can compare the function value at the point 1, 2 with any other value that satisfies the constraint. So basically, you can pick another xy that satisfies your constraint and see if your solution is bigger or smaller than that value. If your solution is bigger, it's definitely a max. If it's smaller, it's definitely a min. So it's this idea that our solution has to be either a max or a min, and so we're going to just compare it with another point. Okay, so in this case, the solution I got, 1, 2, if I take those numbers and I plug it into the function I'm optimizing, f of 1, 2 is 1 times 2, or 2. Okay, so that's the answer I got. And then I am just going to pick another random value that satisfies my constraint. So I'm going to pick any x value I want. I just randomly chose x equals 0. So then if I plug x equals 0 into my constraint, 2 times 0 plus y equals 4, then y has to equal 4. Okay, so the point 0, 4 also satisfies my constraint. But f of 0, 4, if I plug 0, 4 into our function, 0 times 4 is 0. And notice that 2 is bigger than 0. So therefore, the 2 is definitely not a min. So it has to be a max. So this is a maximum. This is the answer we were looking for. So the maximum value of our function is 2. And it occurs when x is 1 and y is 2. All right, let's do another example. Let's see if we can maximize x squared minus y squared subject to 2y minus x squared equals 0. So my constraint is the 2y minus x squared equals 0. Okay, so that's the constraint. We'll call that function g. The gradient of that function g would be negative 2x, comma 2. Those are my partials with respect to x and y, respectively. Okay, so there's my gradient. And then function f is the x squared plus y, or sorry, it's x squared minus y squared. So gradient of f, partials with respect to x and y, are 2x negative 2y. Okay, so then I'll write my system of equations. I'm going to take f sub x equals lambda times g sub x. That's the first equation. And then we'll take f sub y equals lambda times g sub y. And then our last equation in our system is just that constraint, 2y minus x squared equals 0. So I have a system with 3 equations and 3 unknowns. And so in this case, let's see, the first equation, I can actually solve this for lambda. I get lambda equals negative 1 if I divide both sides by negative 2x. And then my second equation, well, if lambda is negative 1, then negative 2y equals negative 1 times 2. So negative 2y equals negative 2, y equals 1. Okay, so I just figured out y equals 1. And then I'll take that 1 and plug that into my constraint. 2 times 1 minus x squared equals 0. So x squared must be 2. That means x would be plus or minus root 2. So technically I have 2 points here. Root 2 comma 1, negative root 2 comma 1. So those are my 2 solutions to this system of equations. All right, then is this a max or a min? One of each? Well, to check, I'm going to take my solutions and I'm going to plug them into the function given. So if x is root 2 and y is 1, root 2 squared minus 1 squared is 1. And then, oh, I get the same thing with the negative root 2 squared minus 1 squared is also 1. So I get the same y value for both of them. So that means either both of them are a min or both of them are a max. And so to check, I am going to pick any other point that satisfies my constraint. So what about x equal 1? So I just randomly chose x equal 1. I'm going to plug that into my constraint. 2y minus 1 has to equal 0. So that means y would equal a half. And then I'm going to take that point 1/2. I'm going to plug it into my function. 1 squared minus a half squared is 3/4. And that is smaller than 1. So that means, yes, they are maxes. And in fact, I have my maximum value of 1 occurs at both root 2 comma 1 and negative root 2 comma 1. Here's another example. Let's find the dimensions of a right circular cylinder, so a cylinder that has a fixed volume V0, so some fixed volume, with minimum surface area. So the constraint is the thing that's fixed. In this case, that's the volume. So my volume is fixed. That's my constraint. The thing that I'm trying to optimize, the thing that I'm trying to minimize is surface area. That's the F here. So to be consistent, I'm going to use the letter G for my constraint. And the variables here are R and H. So again, the constraint is the fixed volume. And I know volume of a cylinder is pi r squared times H. So that means my constraint is pi r squared H equals V0. And I'm just going to go ahead and call that function G. Again, the variables are R and H instead of X and Y. So I'll just write that as G of R and H equals pi r squared H. Okay, so there's the constraint. And the thing that we're trying to minimize is surface area. So my function F is going to be my surface area equation. And the surface area of a cylinder would be area of the top, area of the bottom. That's 2 circles. Plus the area of the sides. And the area of the sides is 2 pi r times H. Okay, so function F is my surface area equation, and that's what I'm trying to minimize. So I'm going to find my gradients. So gradient of function G, and I took the derivative with respect to R first, and then I took the derivative with respect to H. So derivative with respect to R would be 2 pi r H. Derivative with respect to H, pi r squared. And then to find the gradient of F, I had to go in the same order. I did derivative with respect to R first, and then derivative with respect to H. So derivative of function F with respect to R is, let's see, 4 pi r plus 2 pi H. And then my derivative with respect to H, I just look at the only term with the H, 2 pi r. So I have my gradients. So that means the system we're trying to solve is, I took, I guess this is my F sub r equals lambda times G sub r. That's my first equation. And then the second equation I have written down is the F sub h equals lambda G sub h. And then my third equation is my constraint, pi r squared h equals V0. So we're going to try to solve this system. And so I think what I'm going to start with, that first equation looks kind of complicated, so I'll just go to the middle equation. 2 pi r equals lambda pi r squared. I'm going to solve that for lambda. So lambda would be 2 pi r divided by pi r squared. Then we can cancel a pi, cancel an r. So lambda would be 2 over r. And then I'm going to take that lambda equals 2 over r, and I'm going to plug it in to that first equation. So now I've got 4 pi r plus 2 pi h, and then I put in the 2 over r for lambda times, I guess, 2 pi r h And we can simplify this. I'm going to cancel an r out. So that right-hand side becomes 4 pi h. Let's see, I'll put all the h's on one side. So now I've got 4 pi r equals 2 pi h. And then I'm going to solve for h. So divide both sides by 2 pi. Okay, so h has to equal 2r. Getting closer. And then finally, I'm going to take that h equals 2r. I'm going to plug it into my constraint, my third equation. So pi r squared times 2r has to equal v naught. So that would be 2 pi r to the third equals v naught. So r to the third equals v naught over 2 pi. So r is the cube root of whatever v naught, that's our fixed volume, divided by 2 pi is. And then our h value is going to be twice that radius. So my h value would be 2 times cube root v naught over 2 pi. All right, and that's my answer. I'm going to skip kind of checking to see that this is a minimum. It is actually a minimum. If you wanted to verify this, you could. What I would actually do here is just pick a fixed volume, a number for my fixed volume, and then I could pick another r and h that satisfy my constraint, and then compare those values, but it should be a minimum for this one. The nice thing about our Lagrange multipliers is we can extend this process when we have more variables and also more constraints as well. I'm going to just, as my last example, the extension I'm going to show you is something where we have a function of 3 variables and then we have a constraint. So the process is the exact same, and we could extend this to any number of variables that we need to. So in this example, we're finding 3 positive integers, x, y, and z, with a sum of 32, such that p equals xy squared z is a maximum. So my constraint is the fact that these numbers have to have a sum of 32. So that's my function g, and it's now a function of 3 variables. So g is the function x plus y plus z, and that has to equal 32. So there's my constraint, and then the function I'm trying to optimize is xy squared z. And again, it's a function of 3 variables. So how does this change the process? It just means my gradient vectors have 3 components. I'm going to take the derivative with respect to x, the derivative with respect to y, and then the derivative with respect to z. So my partial derivatives for the function x plus y plus z are all just 1. So my gradient of function g is just 1, 1, 1. And then for function f, derivative with respect to x is y squared z. Derivative with respect to y, 2xyz. And then derivative with respect to z is the xy squared. So now when I set up my system of equations, I do have an extra unknown, but I'm also going to have an extra equation. If these gradients are parallel, then I take all 3 of the components in my system of equations. So my partial with respect to x, y squared z, equals lambda times partial g with respect to x. So y squared z equals lambda times 1. And then I'm going to go through and do that for the rest of these gradient vectors. The 2xyz equals lambda times 1. Xy squared equals lambda times 1. And then finally my constraint, x plus y plus z equals 32, is my 4th equation. So although I have an extra variable, I have an extra equation now. So now I have 4 equations, 4 unknowns, And this is still something I'm going to solve. To solve this, it takes just a little bit of playing around with substitution. That's what I'm going to do. I'm going to pick, I decided to pick the second and the third equation. And I'm going to try to use some substitution to simplify this. So technically, my first equation tells me that lambda is y squared z. And my third equation tells me lambda is xy squared. So that means xy squared has to equal y squared z. So the only way that could be true would be, I guess, if y is 0, or if x is z. The numbers we're finding are positive, so I'm not going to even worry about what happens if y is 0. So that means x has to equal z. Okay, so the x and the z values have to be the same. And then let's pick a different two equations. How about equation 2 and equation 3? So both of these equations equal lambda. Lambda is 2xy and lambda is xy squared. So that means the 2xy has to equal xy squared. And then I'm going to go ahead and use the fact that I already determined that x equals z. And so I'm going to replace that z with an x. So that means 2x squared y has to equal xy squared. Again, we're not going to worry about x equals 0, y equals 0, because the numbers we're finding are positive. So let's see, I could divide both sides by, I guess, xy, and I get 2x equals y. Okay, so at this point we figured out x equals z, and y equals 2x. And so finally I can use that information, plug that into my constraint, and solve. So I'm just going to replace the y with 2x. So y is 2x. I'm going to replace the z with x. So that means x plus 2x plus x is 32. So 4x is 32, or x is 8. And then if y is 2 times x, y would be 16. Z is the same thing as x, so z is 8. So it looks like my answer is going to be 8, 16, 8. But let's just make sure this is a max. If I take 8, 16, 8, plug that into the function I'm trying to optimize. 8 times 16 squared times 8. I get like this 16,000 number. So I'm going to pick any other point that satisfies my constraint. So numbers with a sum of 32. How about 1, 130? If I plug that in to my function, 1 times 1 squared times 30 is 30. 30 is definitely smaller than that 16,000 number. So there's no way that 16,000 is a min. It's got to be the max. So maximum occurs when x is 8, y is 16, and z is 8.